Okay, guys, welcome to this final part of combinational circuit. Today, we are going to be looking at binary comparator. As one of those, let us look at a one-bit comparator. This is a digital circuit that takes two single-bit binary inputs A and B and produces three outputs G, L, E. Please note that these are not the actual letters denoting this output, respectively indicating whether A is greater than, less than or equals to B. It uses basic logic gates like the AND, the OR, and the NOT to achieve its function. Consider the truth table for the comparison of A and B with the output G, L, and E. So the output G denotes the cases where A is greater than B, L the cases where A is less than B, and E the cases where A is equals to B, because remember, for any two integers there are only three possible cases when you are comparing two integers. It is either one is above the other, it is either it is lower than the other, or it is either it is equal to the other. Apart from these three cases, until the earth ends, there is no other comparison you will give me. Good. As truth table, this is what we have. The input and the output were labeled. Now, G, which means greater, is 1 only when A is above B. And this is the only case here. So this is what we have. This is what we have here. L, is which means lower, is 1 only when A is less than B. This is the case here. And E, which means equal, is 1 only when A and B are equal. So at this particular level and this particular level, that is what we have. So we have already achieved the cases where G, L, and E can have the output value 1. So the rest 0. That is how we easily complete our truth table. Good. Now let us proceed. If we use SOP expression for G at this particular level, what are we going to have? A, B bar. For L, what do we get? A bar, B. And finally for E, we are going to have A bar, B bar plus AB. And remember, guys, from the breakdown of XOR gates, of exclusive gates, we saw that this is the equivalence of which gate? The XNOR gate, correct? But in this case, you are not going to use the XNOR gate. Remember that if you are being asked to design such a logic gate, you are free to use an XNOR gate for the output gate of E. No problem with that. But in this one, I wanted to use primary logic gates only, although there is a universal gate. Okay, let's understand the logic circuit. L is A bar B. This is A bar and B, as you can see. So this is L, A bar B. G, A B bar. This is my A and this is my B bar. E, on the other sense, E takes what? E takes L and G. Remember that this is, I want you guys to solve this exercise. If you take this particular one, A B bar plus A bar B, then you put a bar on it, you guys should prove me that it is going to give me this expression. So guys, as exercise, make sure you go and prove that AB bar plus A bar B, or that bar, is equivalent to the expression of E. This is a wonderful exercise that I want you guys to come out with. Okay, let's proceed. We're now going to move forward to a 2-bit comparator, but I wanted to explain this 2-bit comparator by using a GC question which was proposed in 2022. And the question says, a logic circuit is designed to have 2-bit binary numbers AB and CD with output E, L, and G. L is high when AB is less than CD. G is high when AB is greater than CD, and E is high when AB is equals to CD. Remember that in our first lesson, we saw that the value high corresponds to which binary input, to which binary digit it corresponds to 1. Okay, A is asking us to draw a truth table for the above circuit. B, that we should determine the Boolean expression for the logic circuit L, G, and E. And finally, C is asking us to draw the circuit diagram of L, G, and E. Okay, now we need to understand. Here we are comparing A and B only. One bit, A is 1 bit, B is 1 bit. But this time around, we are having 2-bit binary numbers, like a number like 00, 10, 11. That is what we have. Okay, guys, this is the truth table we have, because remember we are having 4 inputs. 4 input means that the number of possibilities I must have is 2 to the power 4, which is 16. That is why don't be surprised or don't be frightened by this truth table. Being a member of the byte family, I am going to make everything simpler and chewable for you guys. In which steps? In byte by byte. Good. Let us proceed. You guys need to understand something. Since A, B, and C, D are 2 binary numbers, we have as possibilities. Remember, we are in binary. And in binary, the only digit we can have are 00, which when you convert to decimal gives you 0. We have 01, which when you convert gives you 1. We have 10, which when you convert gives you 2. We have 11, which when you convert gives you 3. Because we are in binary, so the only digits are 0 and 1. And since we have only a group of 2, it means that it is only a mixture of 0 and 1. And these are the only 4 cases we can have. 00 is 0, 01 is 1, 10 is 2, 11 is 3. It is from here that we will know the truth values of L, G, and E. Let me take as example. You saw how I separated A, B, and C, D. Although they are input, but I separated for you guys to better understand. So this 2 gives me 0. This 2, C is 1, D is 0. So this 2 means 10, and 10 is 2. Like for example, at this level, this is 2, this is 0. So AB is greater than CD. When I come here, 1, 1, 1, 1 is 3. Here I have 0, 0. 3 is greater than 0. So this is how we shall easily understand the truth table. We move. We know that G is 1 when AB is greater than CD. And those are the different cases, because here AB 1, CD 0, AB 1, CD 0, AB 2, CD 0, AB 2, CD 1, AB 3, 0, 3, 1, 3, 2. So these are the only cases where AB is above CD. Now we know that L is 1 when AB is less than CD, and these are the different cases, as you can see, because here 0, 1, so AB is less than 0, 2, 0, 3. When you come here 1, 2, 1, 3. When you come here 2, 3. So these are the cases where AB is greater than CD. These are the cases where AB is less than CD. Now E is 1 when AB and CD are equal. Like for this first case, 0, 0, this particular case 1, 1, this particular case 2, 2, and finally this particular case 3, 3. So those are the different cases where G, L, and E can be 1. So the rest, as we saw for one bit comparator, 0. So that is my full truth table. So guys, you saw how easy it is. The base is for you to understand this. You have to understand this, dear students. This is what you have to understand, because from here you can easily deduce what AB is, and you can easily deduce what CD is. And once you have AB, you have CD, the comparison becomes very easy. You simply identify the cases where G will give you 1, where L will give you 1, and where E will give you 1. And now a secret I can give you: on every row I must have only one, a single one on each row. I must have a single one, like I have here, as you can see. As you can see, dear student, there is no row where I will have more than a single one or less than a single one. That is how you can be sure that the truth table of your binary comparator is correct. Okay, we move. In this case, we have up to 4 inputs. It is not going to be easy to simplify it. And since we introduce the Karnaugh map, I think this is where we can make good use of our canopy, our Karnaugh map. Now, mapping the output values of each output to a K-map. Let us start with G. Realize that to map G, this is what we are going to have. Let me just take this particular one as an example so that you will understand the mapping of the other outputs. Okay, where is G1? A0, B1, because this is AB, as you can see. This is CD. So this first one, AB 01, CD 00, AB 01, CD 00. This is the value here. This other one, AB 10, CD 00, AB 10, CD 00, because AB this is 10, CD 100. This is where we are. When you come to this one, AB 10, CD 01, AB 10, CD 01. So this is the value here. When you come here, AB 11, CD 00, this is here, AB 11, CD 00. When you come to this particular one, AB 11, CD 01, AB 11, CD 01. This is where we are, 1101. And lastly, 1110. This is what we have. So this is how we are mapping. Although we saw it when we were doing Karnaugh map, I want to refresh your mind again. Although I am sure that most of you still understand the concept. Okay, let us now try and group the different ones, because as the tradition says on the Karnaugh map, after mapping, what you need to do is group, and we are grouping the larger ones as we can. So the first thing, I have this my square, and now since this one needs to go with somebody, I'm going to pair it with this one, as you can see. And this one too, it can be alone, but since it can be paired with this particular one, I am going to pair them, as we can see. So now we need now the output of the blue, the green, and the red, as you are seeing. That's why I use different colors for you guys to understand each of the output we are going to have. So that is the output of G. G gives me B C bar D bar plus AB D bar plus AC bar. Let me explain. That is why you are a member of the Bi family, and that is why I am here to make things easier for you. Okay, we start with the blue. B C bar D bar. Remember that when we are having a particular group, we identify those that are changing and we eliminate them. First of all, on this one, since my rectangle is already horizontal, it means that CD are maintained, because at this value and at this value, CD are not changing. Now from here to here, A is 0, A is 1. So A is changing, we eliminate. B 1, B 1, we maintain B. So for this particular blue, we are eliminating A only, and we are maintaining A, B, and C. But now, what are their truth values? For this blue one, B is 1, so it is not complemented, as you can see. But for this rectangle, for this blue one, C and D are both at 0. We complement them. Remember that after eliminating the input we have, those that are left, if they are at logic 0, we complement them. If they are at logic 1, we don't complement them. The green, the green is vertical, meaning that A and B are not changing, because at this level A and B 1 1, at this level A and B 1 1. Okay, at this level what is C? 0. At this level what is C? 1. So C is changing, we eliminate it. Look at very well, we are on the green, so this one and this particular one. At this one, we come here, C is 0. When you come here, what is C? 1. It is changing, we cross it. At this level, what is D? D is 0. At this level, what is D? D is still 0. So we are eliminating C and we are maintaining A, B, and D. Now we look at their truth values. A was 1, B was 1, whereas D was 0. That is why we have A, B, D bar. For the red, it is a complete square. So we need to look very well. And I told you guys that when you are looking at these particular values here, you concentrate on what is changing as they are moving. So you cannot be checking for A and B, you compare these two or these two. No. Since you are looking for A and B are moving on a row, so I'm comparing the horizontal values. For C and D, I will compare the vertical values. Okay, when you compare these two, at this level, what is A? 1. At this level, what is A? 1. We retain A because it's not changing. At this level, what is B? 1. At this level, what is B? 0. B is changing. We eliminate it. When you compare now vertically, at this level, what is C? 0. Yeah, what is C? 0. It is not changing. We maintain. What is D? 0. What is D? 1. It is changing. Eliminate. So we are maintaining only A and C. But what is the logic value of A? 1. So it is not complemented. What is the logic value of C? 0. So it is complemented. And the expression gives the sum of the different expression. That is why G is equals to B C bar D bar plus AB D bar plus A C bar. We move, dear students. The output L, this is how it is being mapped. Okay, I want you guys to put a pause on this video and try to obtain the expression of L. First of all, if you have tried, let me see for step 1, if you group as it is supposed to be. The first group, I have my rectangle. The second group, I have my square. I have another rectangle. So these are the 3 groups we have. If you succeeded to this level, congratulations. Let's proceed to see whether you could arrive at the derivation of the output. 1, 2, ta-da! That is L. You see that L is equal to A bar B bar D plus B bar C D plus A bar C. Okay, let's understand. For this blue one, it is vertical, meaning A and B are unchanged. At this level, what is C? 0. What is C? 1. Elimination because it is changing. Whereas D remains the same. Truth values A and B 0, 0, D 1. That is why we have A bar, B bar, D. We come at this level, this particular one, it is horizontal, so C and D are maintained because here and here they have the same value. Here A is 0, here A is 1, elimination. Here A is 0, here here B is 0 and here it is also 0, so we maintain. When we look at the truth values, B 0, B bar, C and D 1, 1, so not complemented. The green one now, when you compare these two, you realize that A is changing. A is unchanged because it is 0, whereas B is changing from 0 to 1. When you look at these two, realize that C is unchanged, whereas D is changing. That is how we obtain A bar C. That is the logic expression for L. We move. For L, this is what we have because we are just taking the cases where they are equal 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0. You see that it resembles the equation of a line where we have as gradient the equation of a straight line. Perfect. Okay. Now, remember that the tradition says what? The tradition is giving us, how will I say it? A rule we cannot apply. Which rule is that? We cannot group the ones diagonally. Also, there is no way for us to like group these particular values in a rectangle, be it vertical or horizontal, because the only way this can be grouped is diagonally. And since it's not possible, what can we do, dear students? Remember that there was a case for it. So how do I do? Correct. If you say that each of the ones should be handled, then you are perfectly correct. So I handle this, I handle this, I handle this, and I handle this. That is what we have. Okay. So what do we get? For the black, AB 0, 0, 0, 0. So this black will give me A bar, B bar, C bar, D bar. This one will give me A bar, B, C bar, D. The purple one, is it purple? Write in the comments what is the color of this particular one, please, dear student. I need to learn from you guys also. At this level, A, B, C, D. And finally, at this level, A, B bar, C, D bar. That is what we have. Okay, guys, let us apply some Boolean arithmetics at this level. in order to simplify E. What can I factor out here? At this level, I am factoring out A bar, C bar. And at this particular level, I can still factor out AC. That is what we have. After factoring out, this is what I'm going to have. When I factor A bar, C bar, here I'll be left with A bar, I'll be left with B bar, D bar, B, D. And at this level, B bar, D bar, B, D, as you can see. But remember, guys, this is a sort of quadratic expression. Let me understand it for you to get very well. So now, at this level, say this bracket and this bracket are the same. It is instead this bracket now, this particular one that I am factoring out. And when I factor it out, I have A bar, C bar, which is left, plus AC. Because remember, if I expand back this, I will have AC into all of this, which is this. And I will have A bar, C bar into all of this, which is this one. And now, these two are the identities of the XNOR gate. That is why E is equivalent to AX NOR C dot BX NOR D. So those are the different expressions for E, L, and G. I hope you understood very well, guys. If not, make sure you indicate in the comment so that I can send you my WhatsApp channel link and we discuss together for you guys to better understand. Remember that we are learning at a fast step and accurately. That is why it is not bit by bit but byte by byte. Okay, guys, after having now the expressions, remember that when we were designing logic circuit, I told you that in some cases where we are going to have many input, like it is the case here, it is important for us to draw the circuit in such a way that each particular input has its NOT beside it. That is how we are going to obtain the logic circuit for a 2-bit comparator, which is what we are having. As you can see, each input has its NOT. Now, let me take G first of all. B, C bar, D bar. See that this AND is taking, this is B, that it is taking, this is C bar, this is D bar. Then this particular one is taking A, C bar, as you can see here. Then this last one is taking A, B, D bar. This one at the end now I have an OR gate adding all of them. That is how you obtain G. Same thing for L and for E. I simply have 2x NOR gate then with an AND gate. So this is the circuit for a 2-bit binary comparator. And this is what came in June 2022 for a whole 9 marks. Guys, I hope you understood very well. This is the end not only of the lesson but of the chapter in general. See you guys for the next video where we shall be treating now GC questions on logic gates and regional mock questions. Remember that, guys, at the end there are exercises that you will be having and there will be a correction that will be done in the WhatsApp or in the WhatsApp and the Telegram channel. Also, a link will be provided to you where you will go and exercise yourself, where you will be answering MCQ question and at the end you will be giving your score. Thank you for watching. Be a member of the Bio family. Do not forget to like, subscribe, and share it to your classmates so that our community can grow for more and more videos of this kind. Thank you very much.